Okay, the recording has been started. So hello, everybody. Thank you for joining us today for AIAA Los Angeles Las Vegas section town hall meeting. Today we have very exciting topic, and there was a great speaker going to talk about very exciting activity for on-orbit servicing. But before that, we'll have a few words for logistics. So first of all, we thank Lomita Library for providing this is a wonderful meeting room. We did it here before in 2019 for space architecture event here, a mini conference with some speaker from JPL and USC, Professor Martu Sankapenu, and Melody Yasher, award-winning designer for Mars X House. And so we are so happy to get back. I really appreciate it. And I also thank AIAA for providing us this great organization support. The other thing for the in-person attendee here, you have the coffee over there and bottled water, donut, and cookies. Please enjoy. For online folks, I'm sorry, we are trying to get you here in person to enjoy the food. So next time, please show up. The restroom is behind you, so you can take a look. So we have some glider and the brochure for AIAA membership. Before we start, we have something leftover business. So last week we have a presentation by Dennis, Mr. Dennis Liang, and I forgot to bring the appreciation certificate. So thank you, Dennis. So let's make sure we don't forget. Thank you. And Dennis will give a talk next week, November 4th, in Longdale Library. So please attend. And online we have Dr. Dominique Valentien, who was a speaker from France on October 7th about Venus. Exploration lander on Venus. Maybe there's something our speaker can take interest in Venus using his wonderful robot. Dominic, want to say something?
Oh, no.
Just say hello. Very good. Thank you. Dominic is from France. He's our AIAA Associate Fellow. And online, we also have a distinguished guest, Dr. Rich Van Allen, who is working nearby, microcosm. He's just had 50 years of AIAA membership. So we recognize him, and he used to be our council section chair. And of course, the company also with Dr. James Worth. So Rich, do you want to say a few words to our attendee speaker here? Well, if not, we can wait. So we really have great membership here. So if you are not yet a member, please consider. If you haven't renewed, please consider renew the membership. It's a great organization. So without further ado, our speaker today is a manager in this called GITAI USA. This is company doing great jobs doing the on-orbit servicing using robot. So he's going to tell us his new development and the company capability. And if you and your company have certain interests, you are welcome to contact him. It's also for students, also very good opportunity to learn, and they might have internship opportunity. He will tell us more. Yeah, he will be able to introduce himself much better than me. He was, Alabama, Stanford University, great education background, a lot of experience in aerospace industry and robotics. So without further ado, let's welcome Mr. Seiya Shimizu.
Yeah, so thank you very much. Thank you very much for a great introduction, and I'd like to extend my gratitude to everybody who joined us today in person and of course online. So again, my name is Seiya Shimizu. I am the project manager of extravehicular robotics tech demonstration at GITAI USA. So before starting my presentation, please allow me to give you a brief background on myself. As Ken just mentioned, I obtained both bachelor's and master's degree in aerospace engineering, focus on the satellite systems engineering. But after this, I took some data from the space industry for about nearly a decade. I started my career as an avionics engineer for an fighter aircraft program in a big enterprise. After dedicating 5 years there, I transferred to a startup who was at the forefront of the development of the autonomous mobility platform, autonomous personal mobility platform. But the 10 years I spent over there was really great. I enjoyed engineer life over there, but I cannot forget about my childhood dream. The dream to make contribution to space industry, to expand humanity's envelope to outer space. That passion brought me back to the space industry 2 years ago, and I found my home at GITAI. Since 2021, my team at GITAI has been working on the development of the robotic arm for on-orbit servicing missions, and we are lucky enough to secure an opportunity to send our robot to the ISS early next year. So that mission on the ISS is technical demonstration for our robot called S2 to showcase our capability of building extravehicular robot technology. So we already handed over that payload to NASA last August. Then we eagerly await its launch in coming January 2024. Today, I'm honored to introduce part of my work to you. So everyone, please welcome our GITAI S2.
I'm sorry, before you start, you can share the PowerPoint.
Oh, sorry. Oh, is it?
It's not shared.
It's not shared. Now everybody can see my screen.
Folks online, can you see the presentation online?
Yes, it came on now. Thank you.
Oh, sorry about
Yes,
it.
it's okay for me also.
I forgot to share screen, but now it's fine. So let's start. Right, thank you very much. This is S2, the second space robot we made, and the first extravehicular robot for us. The launch is scheduled for January 2024, and we will initiate the experiment in February. The robot will stay on external experimental site on the ISS for 6 months, and then after the 6-month experiment period, it will return to the Earth for the further verification or further investigation about what exactly happened on our flight hardware on the external space environment, a very harsh, high temperature cycle environment, and including also radiation and vacuum environment. So I hope I can have another talk a year from today about the outcome or the result of the experiment. S2 plays a very vital role in our company. It acts as a significant stepping stone of achieving our mission of providing a safe and affordable means of labor in space. The rise of new space launch providers such as SpaceX, Rocket Lab, Firefly has significantly reduced the cost of space transportation. However, the cost of space development remains high. Why? Because the cost of human labor remains high. To send a human to space safely, we need to invest a considerable amount of time and money in training, equipment, and procedures. So this approach is not sustainable. To expand our life sphere to the Leo, Moon, Mars, and beyond, we need to enhance our work capacity or work capability exponentially. Sending a large troop of human labor to space is not economically viable. The only solution is to use a robotic labor. That's why we are here. That's why GITAI moved the entire company to the United States. We opened our facility in Torrance last year and established full R&D and manufacturing capability. Currently, 90% of our employees works at the Torrance facility. We prepared a 1-minute video clip to introduce our facility, so please watch. It's a very silent video anyways. So it's located in 2255 Dominguez Way, Torrance, California. So it's actually just 10 minutes from this Lomita library. We have the ground test environment, including space station mock-up or some other environmental testing facility to test our robots in 1G environment. We have an inchworm type robot arm and a rover and several other types of robotic arms too. So in the GITAI portfolio, we have multiple types of rovers so that we can provide different types of space applications. We can provide robots to different types of space applications. This Torrance facility, we developed space robots for 3 application domains. One, there's space station support, on-orbit servicing, and lunar city construction. S2 is designed for on-orbit servicing missions, and GITAI also has other types of robots for space station support and lunar city construction. These robots share the design of key components, the key technological components with S2. So technologically, all of GITAI robots are brothers and sisters. So all the GITAI robots are designed based on the key technology we developed internally. The GITAI has a strong philosophy on vertical integration. That we design and build both hardware and software internally. So I brought some hardware I brought some sample of hardware here at Lomita Library today. So I put them on the front table. So after the presentation or whenever, please feel free to take them and see them. Now, some of them are very heavy, so please be careful not getting injured. But they are actual hardware, but they are just samples. Feel free to touch with a bare hand or something like that. The strong engineering team at GITAI enables us to keep the vertical integration culture. The majority of GITAI engineers hold PhDs in robotics, focusing on wide variety of fields. We have experts in the motor controller, power electronics, actuator, and end effector, as well as software components such as computer vision, motion planning, network, database, and robotic system integration. Thanks to this in-house expertise and hard-working culture, we achieve rapid development cycles. For example, S2 took only 2 years from the project kickoff to the payload handover. It was extremely short compared to other space programs. But still, it was the longest project in the GITAI history. The typical, it took longer than other GITAI projects because we need to prepare for the NASA safety review, where the typical development cycle of a robot at GITAI is from 6 months to 1 year. So now let's talk about the GITAI S1, the oldest brother of GITAI space robots. S1 is a semi-autonomous, semi-teleoperated robot designed to conduct astronauts' tasks, daily tasks such as switch manipulation, scientific experiments, and equipment assembly. S1 successfully completed all the technological demonstration missions in the ISS in 2021. S1 was installed on the internal wall of the Nanoracks Bishop airlock. And the robot was controlled from Nanoracks control facility in Houston, Texas. After the mission, S1 returned to the Earth, and the actual flight unit of S1 is now on exhibit at GITAI's Torrance office. I have a 5-minute video clip for the overview of the achievement of the S1 project.
Back with you, glad to see you back with us. Just want to give you a heads up before we go into this big LOS in about 5 minutes. We did want to check out the connection of that J29 connector.
The room the experiment was conducted is one of the airlock that the ISS has. The commercial company called Nanoracks has their own airlock on the ISS, and we rented their facility, on-orbit facility to conduct our demonstration. And the view right now is some part of the user interface that the ground operators see.
What is that simulating? Is that a structure that might be built on the outside of?
Yes, yeah. So it's kind of mimicking the in-space assembly and manufacturing type tasks, robotic tasks, including the antenna or the solar panel assembly. That could happen on the outside of the station. Yeah. So the S1 is equipped with a computer vision and some computer vision software. So it actually detects the location of these the switches or other the components by itself. So it can run the task autonomously too. And also it has the capability of doing the teleoperation via haptic user interface.
Question.
Yes, sir.
So, first of all, how many joints do you have in this arm? And second,
What was the first question? How many right?
how many joints do you have in this arm?
How many joints? How many joints? Okay, the arm is 8 DOF, 8 degrees of freedom.
Okay, so the number of joints are 6 then. Would that be correct?
I think 8. For S1, I think we have 8 joints. Plus
8
one
joints.
gripper. Yeah. I'm gonna double
Okay.
check, but yeah.
Generally, the degrees of freedom are essentially less than the number of joints, but that's
Oh,
okay.
sorry. I mean, the joints of the L-shaped joints, maybe. Yeah, sorry, you're right. One or two actuators is included in the link. So actually the number of joints are less than that.
So is this operation that you're showing, is it autonomous or is being controlled by through Houston?
We have that robot has both capabilities. It can run the full experiment autonomously, and you can control the robot from Houston by human haptic interface. I think there's a video. Yeah. Does it answer your question? Okay, on this video, we don't have the coverage of the haptic interface, but we have a dedicated in-house designed haptic user interface to control the robot on the ISS directly from the control center in Houston.
Thank you.
I have a question also. Is it internally powered or does it require power from the ISS?
That particular one requires power from the ISS.
What about externally if it goes out into the for a spacewalk? Is that also requiring the ISS power?
For the long term, yes. The interim type spacewalk, yes. Yes and no. Actually, well, I can talk about it later, but we have several types of robots. So let me divide the question into two. For our S2, the extravehicular tech demo mission robot, does not have a capability of work, and the power is purely supplied from the ISS. So it doesn't have any battery or other energy storing devices on the robot itself. And for the interim type robot we have developed has an internal battery for the standalone capability, standalone work capability. But the battery is not that big enough to cover the entire mission life cycle. So it's like a charge and discharge cycle on the ISS. Not on the ISS, but any kind of a space station, including commercial.
Okay, so one more question.
Yes.
What are the load carrying capabilities of this S1 robot that you showed? Load and torque both.
Pardon me? Lower.
What are the load carrying capability of the robot?
Well, actually, the specification of robot we can talk about later, but give me 1 sec, I think. Yeah, the actuated pitch focal is around 30 Newton meters, but as a robot, we need to limit the torque and angular velocity of each joint to satisfy the safety requirements. It's very limited. And I don't have the exact value right now, so.
All right. Thank you.
Right. After the success of the S1, the success of S1 led us to another technological demonstration on the ISS. That is S2. The S2 will be installed on an external experimental site on the Bishop Airlock. The robot will stay on the external surface of the ISS for 6 months, and it will perform multiple robotic tasks. We will conduct the full task demonstration once every week, and between the two demonstration sessions, the robot will continue moving for the endurance testing. The telemetry data of the robot will be continuously downlinked to their NanoX facility and transferred to our Torrance facility for the 24/7 monitoring. For S2's operation, we need only 2 ground operators and 2 laptops, 2 general laptops, not a workstation or customized superpower laptop. S2's control loop is called supervised autonomy. The robot is equipped with 2 onboard computers which accommodate all necessary software packages, including computer vision, motion planning, and motor control. S2 is capable of executing all the tasks autonomously. However, for this particular experiment, we added a human interaction in the control loop. The robot asks human for go or no-go decision for the key steps at the robotic tasks, and the human operator in the control loop has a graphical user interface to monitor S2's current status and the future trajectory that was calculated on the ISS. Then human operator, based on this information, the human operator sends go or no-go decision, go or no-go command to S2 to execute or to abort the step. So I have another video clip of the S2 ground operation demonstration. After it gets installed on the ISS, it will deploy to the task operation mode. And on the payload, we have several task units, what we call the busy port, the subset of the robotic operation. The left of the camera view is actually the camera view of the computer vision camera equipped on the end effector. So that camera view has the ground operator has that camera view. in addition to that, the 3D model representation of the robot posture, the exact posture of the robotic arms.
You testing that in the thermal vac chamber?
Yes, we did. Yeah. For the entire system, yes, and each subcomponent, including the RCU, the robot control unit and arm, yeah, we put into the TVAC chamber and for the testing. This experiment contains the 6 different robotic tasks.
Can I ask a question? Hello?
Yeah.
So was the robot packaged for the launch by your company?
What do you mean by the sponsor wise or technology wise? But
No. So this was launched in a launch vehicle, as a payload.
Yes.
So you did the packaging for the robot and tested it?
We did the packaging, and for the actual final packaging was done by Leidos, the NASA CMC contractor. But we provide the basic instruction. We provided basic packages and provided the instruction of how to package it for the to load onto the Northrop Grumman Cygnus vehicle.
Okay, so it was launched on the Cygnus vehicle. All right. So was it?
Mm-hmm.
So the robot required any assembly once it got to the orbit, or after it was captured in the space station itself? Was it deployed? Yeah.
It was a good question. It's a very good question. And well, how to say it? Let me skip a little bit. Okay, good. So the robot will be launched as a pressurized cargo to the ISS. And the astronaut will assemble the robotic payload package into the actual deployment configuration, the left-hand side picture, in the ISS, in the NanoRax Bishop airlock. Then the robot will be installed to the external experimental site by using the ISS robotic arms, including the SSRMS and SPDM. So after it got deployed, the robot does not need any EVA by the astronaut. But before deployment, inside the ISS, inside the pressurized area, the robot requires some assembly, not very complicated, but some assembly procedure is included.
Okay. So you said the power source is ISS, so it will be connected. Yes. It would be powered by the mobile transporter bus, or would there be a separate what you call effector on the station itself, where it will take power from?
On this page, you can find the 2 oceanering go-to connectors. One on our payload side, the very left bottom of the page, oceanering go-to active HARF, and on the airlock side, they have another oceanering go-to connector, which is passive HARF. They are the robotic interface for the external payload, and that connector has the capability of provide a 120 volts power source from the ISS. So electrically, the payload is connected to the ISS power source via the oceanering go-to.
Okay. And this is a continuous connection, right?
Continuous connection, yes.
Thank you.
Yeah, so let me step back one page. So the experiment contains 6 different robotic tasks. These tasks mimic important technical aspects of real-life on-orbit servicing missions. The ORU, on-orbit replacement unit, manipulation, tool changing, fastener tightening and removal, the thermal blanket manipulation, connector mating and demating, and the dual arm cooperation. even though this experiment will be conducted on the ISS, but these technical aspects are common for missions on any kind of free flyer platform too. For example, satellite life extension mission also requires connector and fastener handling motions. So S2's experiment will showcase its dexterous robotic capability for the multiple types of on-orbit servicing missions. And yeah, we can back to this picture. So this is a closer look to the S2 system design. Each arm has 7 degrees of freedom and an end effector. And each end effector is equipped with 2 computer vision cameras. So we have 4 cameras in total as a system, in addition to the 7 cameras for the recording purpose. No, not 7, 3 environmental cameras for the recording purpose. The box below the arms is a robot control unit, RCU, which contains the power distribution unit, power control unit, and onboard computers. And you may notice that there's a black cage, and that cage is also part of the payload. It's not a robotic payload, but that cage is designed and provided to protect the ISS for any kind of potential damage by the robotic arm. So of course, the robotic arm itself has multiple layers of safety features to preclude any potential damage to the ISS. But for additional safety layer, we added the kind of the physical barrier to the ISS.
Question?
Yes, sir.
Can you talk about the communication system it uses to connect with the ground control?
Ground control, at first, the robot is connected to the ISS local area network via Ethernet. And from the station to the ground, the ISS control uses, I think, Ka band for ground communication. Then that kind of the data packet is tunneled to the NanoArt facility.
Okay, and is there a time delay at all between?
Yeah, there is, but actually that is not significant.
Okay.
Yeah. Well, we will see. I mean, from the past experience with S1, we saw that the delay or the latency is not that long, but the S2 will be launched next year, so we will see what would have exactly happened on our S2 part.
I see. Thanks.
Is it a Bluetooth connection?
No, there isn't any Bluetooth. It's purely wired connection, wired Ethernet. So we passed the final safety review with NASA ISS safety panel last June, followed by the final preparation for packing. The GITAI team conducted the end-to-end functional verification at NanoArt's facility in Houston and handed over the payload to NASA CMC in August. The end-to-end verification included the remote operation test from NanoArt's facility, NanoArt's control room, to the ISS, which was connected to the NASA JSL Joint Station LAN test bench located in the NASA Johnson Space Center. So we simulated the entire network loop from the NanoArt facility to the ISS on ground, and I really express my gratitude to NASA JSC and Marshall Flight Center for their tremendous support of making it happen for our payload. So, Northrop Grumman Cygnus. In this coming January, the S2 will be launched from Kennedy Space Center on NG-20, the 20th flight of the Northrop Grumman Cygnus spacecraft. I retrieved this photo from Kennedy Space Center's website, and this particular one, this is the Cygnus NG-20, which carries our S2 to the ISS for us. So thank you very much for the Northrop Grumman, the great work for providing us the launch opportunity, the cargo area for our robotic payload. So if the launch and installation go smoothly, we will initiate the experiment in February 2024. So we will post the updated. So please stay tuned about our future outcome about our S2 payload. Okay. In addition to the space-ready robots, space-ready robotic arms, we developed rovers and inch-run robots for ground demonstration of robotic capability for lunar city construction. With robot arms, the rover is capable of handling multiple objects in a sandy environment. So let me introduce a robotic fleet tested at Dumont Gene, California. This is the group photo of the current GITAI's robotic fleet. The multi-robot cooperation will be necessary to build a large-scale construction. We built multiple rovers and multiple robot arms and started field experiments to show how the robots are useful for lunar city construction. We brought our robots to the desert and conducted the field test of multi-robot collaboration. Please enjoy the video coverage of the desert experiment we conducted last March. This field experiment was kind of tough for human beings, but it was very fun part. Thank you.
Okay.
In addition to the field, like the multi-robot collaboration part, for the real-world lunar exploration, the countermeasures to the lunar regolith contamination is a very key part, another key factor of the development of robots, development of lunar robots. We also built a regolith chamber facility at GITAI USA office, the GITAI Torrance facility, featuring 7 metric tons of regolith stimulant. In that facility, we conducted the comprehensive testing of our GITAI's the inchworm type robotic arm and the GITAI's lunar robotic rover. The robot successfully accomplished multiple tasks and operations. The first task were 2 changer demonstrations of sampling lunar regolith using the backhoe type tool and sampling stones using the gripper type tool. The second task was inchworm working demonstration in the dusty environment in the lunar regolith chamber. And the final one is the rover locomotion demonstration. This is actually the static picture of the locomotive demonstration. We prepared another video clip for you, but we'll check out the lunar regolith chamber experiment. So this is the lunar regolith chamber we have in the Torrance facility. This white sand here is actually the lunar regolith signal, not the test sand. As you may or may not know, lunar regolith is very fine particle and can be hazardous to human life. So we took very carefully. We handled the sand very carefully. I was not in the chamber itself, but the lobby over there was our mechanical engineer and who really wear the protective suit and got into the chamber.
What did you use to simulate the regolith?
The regular stimulant. It was the commercial regular stimulant, LHS1, I think. We bought them from the Exolith laboratory located in Florida.
Do you have some idea if the robot operates in the environment for an extended period of time, whether the fine grains of the regolith might disrupt the machinery?
Oh yes, exactly. The it can disrupt the mechanical parts by the kind of getting into the moving parts and disrupt any kind of the cause more frequency, more friction.
Okay.
And finally get it gets broken. Actually, we did the chamber test I showed you today is a more system-wide end-to-end test, but we also have a small-scale chamber for the endurance testing, how the lunar regoliths can affect on the mechanical and electrical parts too.
Okay.
In the long term.
Do you have an idea of what the lifetime might be before it needs to be?
I don't think we have the exact number yet. Right?
Okay.
We are still evaluating, so I don't have an exact number I can disclose to you.
Question regarding the on-orbit robots.
Yep.
Have you done analysis for mean time between failure for these robots up in space? And let's say if you do have a failure in one of the not just the motors, but in fact, you lose a discrete component up in orbit, your whole motor driver will be shot. What is the plan first of all, is there a plan to do on-orbit repairs, or the whole robot has to be brought down to be repaired?
Well, we don't have any plan for on-orbit repair for our payload. I think you're talking about our S2, right? The LEO experiment.
Yes, the S2 and even S1, it applies to that too, but that would be much easier to repair in orbit because it's in the pressurized space. But an orbit that you're going to hang off the truss element, or I don't know where you are going to put it, or somewhere out in the on any other payload facility that the ISS provides. So you're not telling me that it's a one-shot deal. It fails,
Okay, yeah. Well, let me explain. We assume, this will be the first experiment on the ISS, not extravehicular environment on the ISS. So we haven't had any experience, but we assume that the major causes of any kind of the failure mode of the robot is the radiation effect. And we evaluated the possibility of that kind of effect, and we concluded that most of the failure mode that could happen on the ISS can be recovered by the electrical reset of the entire system. So the possibility of the permanent failure, the permanent break, is negligible for us. And given the full experiment duration of 6 months, if our experiment is much longer than that, we need to consider the repairment method or something. But we concluded that we will not need the repair plan for that. And we have some redundancy in the robotic system as a whole. So even if some of the payload components got broken, we can still detract the payload into the ISS again safely to return the payload back to the Earth.
So what you're saying is that you have redundant electrical parts, paths, not parts, paths within your electronic control unit, as well as mechanical systems that you're building. If one fails, the other takes over. Would that be a correct assumption?
But yeah, of course, the design philosophy under S2 is protect the ISS facility and ISS crew. So anything, we implemented the necessary redundant necessary redundancy on the entire system, so that it will not break any ISS components, or it can damage to prevent the potential damage to the human body of the ISS crew. But the failure mode that causes the termination of our experiment is not critical or not catastrophic to the ISS, the entire ISS environment. So we took a risk that there is a possibility that we have to stop the experiment at some point in the 6 months experiment period. As long as we can detract the entire payload back to the ISS, it is something what included in our expectation.
Okay, so that is a known risk, you're saying?
Yes.
Okay, thank you.
Mm-hmm. Yeah, thank you very much for your question. It's a very good point.
One question.
Yes.
What the temperature range you assume for the specification of this?
It depends on the orbit and the surface. If you're talking about the LEO or the lunar surface, but for the S2 case, the assuming temperature range, the temperature range of the robot unit is from -60 to +80.
Seriously?
Celsius, yes.
Oh.
Yeah, because there are several variables, the determining factor of the temperature. But based on the characterization and based on the information about the ISS orbit and the passive and active thermal protection we have on the on the robotic payload, we assume that the storing temperature and the storing temperature of the robot will fall into the range of -60 degrees C to the +80 degrees C.
80 degrees.
80, yeah.
That's also on the surface of the moon?
No, the surface of the moon is a totally different story. So yeah, we need to do the thermal design from scratch for the lunar surface application.
Thank you.
Yeah, I have a question. On your system, it seems fairly very sophisticated robotics. So do your manipulator effector tools, do they use some type of like force feedback sensory units in order to determine when you're manipulating objects? You know, does it provide some kind of a tactile sort of feedback to confirm, for example, the grasping of a particular object or something to that degree?
Yeah, it's a very good question, and yes, it does. On the wrist part of the end effector, we have a force and torque sensors. It's a 6 DOF force torque sensor to evaluate the actual force and torque applied on the edge of the end effector. So the robot can evaluate if the robot is physically contacted to the target object or not.
Yeah, I would have thought that would have been pretty necessary. And also, just out of curiosity, due to the success that for example the Mars mission with the what is it, the Ingenuity, the little flying robotic helicopter that they have there, and also the kind of upcoming mission by NASA, the Dragonfly mission. Are you planning on perhaps building some type of a helicopter or flying platform for say for Mars? I mean, that's being used in Mars right now. Is your company planning on maybe going in that direction at some point?
Yeah, a good point. Actually, we are very interested in doing that. Honestly speaking, we don't have any solid plan of doing that, but personally and as a team, we are very excited about that kind of opportunity. But as a company right now, yeah, we don't have any plan to build a helicopter or drone, the multi-copter type robot for the extraterrestrial body right now. But again, we are very interested in that, and we have some, well, we have an engineer who came from the multi-copter industry, so I think we can try it at some point.
Yeah, that seems like a very exciting sort of new sort of opportunities for robotic systems, especially on planetary missions that have where you have atmosphere, obviously, or flight, like as I said, the one for Titan and Mars. But just curious if that was a direction that anybody had any interest on. Thank you.
Mm-hmm. You're welcome. Good question. What was the last page I talked about? Oh yeah, this one. Okay, the videos I showed today, the slide I showed today is everything is the kind of self-funded technology demonstration mission, because we don't have any NDA type thing for the internal tech demonstration missions. But in addition to these kind of self-funded missions, we closely work with government entities and the commercial space companies. The one example is DARPA Lunar 10 project. GITAI has been selected for a contract negotiation by DARPA for the 10-year lunar architecture capability study. The short abbreviation of that project is Lunar 10. This research will allow humans to build infrastructure on the surface of the moon with multiple autonomous robots. We are honored to be a part of the state-of-the-art research program with other excellent companies. Okay, and that is a very important slide for me. So to expand our business, we need more colleagues. It is the most important message I have to carry today. So we are hiring. So we have open positions for the project manager, mechanical engineer, and the financial and the business development. If you're enthusiastic in robotics or space systems or both, we can provide a very challenging and fruitful opportunities. And we also have internship positions. So if you're a student or a young engineer who are seeking internship opportunities, please contact our HR team via LinkedIn. So this is a link to our LinkedIn page and other company resources. Most of the videos I showed today are listed on our YouTube channel. And also, as mentioned earlier, our office is located in Torrance, so it's just 10 minutes away from here. So if you want to apply for an open position, or if you're interested in our technology as a customer or as a potential business partner, then please feel free to contact us. We can arrange some kind of a facility tour for you. So that's everything I have today. Thank you very much for listening, and thank you very much for the question I got today. And of course, I have more than 20 or 30 minutes free time, so I'm free to answer your questions.
I had a question.
Yes, sir?
See, on the S2 robot,
Yeah.
is the baseline design for that to be fixed on the external surface of the space station? Is there an option for a mobile version of it that can free fly around the space station and to service any portion of it?
Yes, good point. Yeah, well, I kind of separated the technical aspects, but first of all, the design, the robotic design requires kind of the fixed point on the one end. Well, how do I explain? The component-wise, the S2's key components, including the motors or the motor drivers, are common with the inchworm, the spacewalk robotic arm. So it's very easy to migrate one from the other. Not super easy, but relatively easy. to migrate one design to the other type of the robotic arm compared to the designing something from scratch. But the S2 design is based on the assumption that we can have a fixed point on one end. So it needs to be, the robotic arm needs to be attached to something. It doesn't have to be the space station. It can be the spacecraft platform, the free-flying spacecraft platform, to provide the mobile repair or inspection capability to the commercial station or some others. So yeah, the robotic arm, as a robotic arm, requires the mothership, but any kind of mothership, including space station or the spacecraft or the satellite bus, can provide capability of the mobility to the robotic arm. Does it answer your question?
Yes.
Regarding the lunar vehicles, I'm curious if there's a particular type of structure that the robots are optimized to create. I noticed there are certain procedures that you were showing, like, placement of the walls and welding them together, etc. And I'm wondering do you think the robots are optimized to assemble in that way, or is there is it possible, and if there was a different type of structure that was proposed, that the robots could handle that equally well, or what? In other words, what I'm asking is there a type of lunar base that these robots would build quicker or better or more efficiently than another type of base?
Robotic friendly structure or something like that, other than the general type of general type of structure. We believe there must be some kind of robotic friendly structure design somewhere.
Okay.
And we have internally we are running some kind of research and development to find what kind of robotic interface, what kind of interface or structure design is robotic friendly. So of course the very general construction methodology we have right now is not robotic friendly.
Right.
And for the lunar surface or Mars surface, we definitely need some portion of the robotic friendly interface, and we are very interested in developing or seeking the third-party interface possibility to make the world more robotic friendly.
So the inchworm robots that you showed in the video, they required some sort of attachment point.
Yep.
Are those attachment points already present on the ISS, or do they need to be mounted? If they need to be mounted, how difficult is that to do on the ISS?
That's a good question, and I don't know if I have a picture of that.
I think the mounting points were shown on the.
Oh yeah. Oh yeah.
Yes.
They are, how to say, they are the prototype design and built by ourselves. So it's not deployed to any kind of space station right now yet. And of course, there's a room for maturation, I think. But I think that's how do I say? Mounting this kind of grapple fixture to the current existing station, like the ISS, is not very economically viable. But we haven't, we are seeking an opportunity to put this kind of the grapple interface for the future space station, future platform. I'm not sure if it's a good wording, but the downside of the current grapple fixture on the ISS is that it's very big, it's massive and very expensive. So I think for the future commercial program, for the commercially viable space program, we as the industry need some kind of the replacement of the robotic interface, and that is an option we are proposing.
Have you considered? Oh, sorry.
Yeah. In regards to mission-oriented decision making, how do you choose what sorts of tasks you use the machine for, as opposed to like using conventional? Is it for like optimizing for time, or is it for they want prevent human exposure?
For the astronaut support or the space station support type robotics, we analyze the time consumed by the astronaut. I mean, that we have a kind of some sort of the time astronaut, the daily timeline basis, and I think it's not it's very widely known, but there are about 30 or 40% of the astronaut timeline is consumed for the very non-technical standard daily activities, including some opening some bags or something, and cleaning up the space station or something. And that kind of the simple task can be replaced with robots. So we decided, of course, the S1's task design is tech demonstration, and we just selected some the most important, the most time consuming task, but that kind of the dexterous motion can be applied to any kind of the astronaut's daily life.
I was going to follow up on the question about the inchworm attachments. I was wondering if you've tried to replace them with some kind of like other way to, like some type of adhesive or suction cup or something that might not require the installation of those fixtures. Has that, have you considered that?
Material-wise, or what? So the question.
Well, currently now you have an attachment from the inchworm and you have an attachment that's installed.
Yep.
Have you considered replacing them both with just a flat wall and maybe some way that it can stick to the wall?
Yes. It's possible. So you mean the putting this the fixture to the flat wall?
Yeah. Like
here or there.
Yeah, exactly.
And
is that possible?
sliding the
Using
wall.
magnetic or
Yeah.
vacuum or something, some other thing that doesn't require
Non-mechanical
interface.
Non-mechanical interfaces. Well, we haven't considered the non-mechanical interface yet. Yeah, everything is we designed is mechanically fixed. Yeah, because of some other limitation coming from the actual application, like the catching the free flying, the visiting vehicles or something like that. To make it, we need some kind of secure. We need to grapple the target object securely. So anyway, we need kind of the mechanical interface.
Regarding the those attachment points,
Yes.
aren't there some currently attachment points for the robotic arm that's actually being used in the ISS currently? Would there be a possibility of you utilizing those, or is that just not a compatible to the current design that you have?
Well, the grapple fixture on the ISS is designed for the end effector of the Canadian the SSRMS, but mainly the compatibility is a design matter of the end effector only. So what how do you say it can be separated from the arm design. So if we have if we have an end effector which is compatible with the current existing grapple fixture on the ISS, yes, our robotic arm can work on the ISS. So and the end effector design, I'm not sure. Yeah.
Could you design some kind of an adapter to fit your unit and then utilize those existing external attachment points?
I believe technically it's possible. what I don't know is how it's protected by the patent or some kind of the legal protection.
Oh, I see. Right. Okay. Of course. Yeah. Right.
Yes, Ken?
Is your robot system need to go through vibration or shaking acoustic testing before launch?
Oh, yes, we do. Yeah.
We do?
Yeah, we did the environmental testing, including the TVAC, the thermal, and vibration.
You know, some company like Aerospace Corporation, you know, they're very good, you know, doing this kind of testing, evaluation, also Roman too. It's very important. And then, you know, the robot system probably also have, you mentioned avionics, you know, there probably some chips, something like that. Are they radiation hardened for space mission or like a cast off the shell?
They are parts, commercial of the shell components, and we evaluated most of the key electronics for single event effect and both TID, total TID. Anyway, yeah, both long-term and short-term effect of the radiation. Yes, so they are not radiation hardened, but we concluded that they are radiation tolerant.
So for those testing vibration and in-house, or you somebody outside test it for you?
We outsource, especially the radiation test. We outsource. Yeah.
Oh, okay, yeah, very good.
We don't have any radiation source in house, unfortunately.
Is this system, whether S1 or S2, ever being used or demonstration for like servicing of satellites or refueling? Have you guys ever thought about that?
Very good point, and that is the one we are going to do after S2. But the robotics wise, it's the robotic capability is something what we already have, I think, for the referring function or something, like capturing the free flying object and applying some kind of assembly or de-assembly task on the free flying platform. We have a robotic capability, but I think the the technical aspect we currently don't have is the satellite bus side or the RP or the rendezvous and proximity operation capability.
Right.
So we are looking for some kind of technology.
The reason I ask, I've spent 20 years building satellites, and out of those years, I've seen all different kinds of designs, and every single one of them is not designed to be serviced. So it's very, very difficult to service anything that's currently up there right now because they're in different positions. It's very hard just for your own hands to reach and get into. Are you guys also working with NASA or any other government organizations or decision makers so that when they put out their proposals that they do have like a servicing requirement and using this particular type of technology so that the design is meant to be serviced with, you know, this kind of technology? Are you guys working at any kind of like policy influence with agencies?
At least what I can say is we are a participant of the conference, and I don't remember what exact other organizations or entity we are involved in, but yes, and partially yes, and we are getting into the policy decision type stuff too. Yeah.
Regarding to the public policy issue, just want to mention AIAA, Dr. Ben Allen also know very well. Each year we have what they call Capitol Visit Day to the Congress, to the national capital. And it's not for individual lobby, you know, for specific company or something like that. But if it's some public policy issue, our local chapter, LA, Las Vegas, or national, they have a public policy group. So if you want to lay out some kind of general like office servicing or some kind of public policy, we are welcome. We can work together. And we also have technical group So if you would like to kind of release certain kind of white paper, something like that, you're highly welcome. That's why AIAA exists, is to facilitate this kind of discussion.
Because I'm listening to a lot of the questions that's being asked, and a lot of it really boils down to how do we implement this kind of technology in either our current hardware and or future hardware. And so if we keep going the way we are, people are just going to keep designing whatever they want, and it doesn't really match up with anything, right? And then so we're constantly trying to chase after them. And so, is there any kind of, going forward standard that everybody can say, okay, just like in the aviation industry, right? Every airport you go into, the fueling is the same because the connectors are the same. We all understand that. And so I think like in this industry, we really need to start moving forward to have some kind of standardization going forward for like maintenance and repair and so on and so forth.
Yeah, right.
So that's why I was like, I asked these companies to see if, you guys are working actively with anybody else to make sure that happens.
Go ahead.
Yeah, I was wondering.
I have a question. Sorry.
1 second, Sarah. Wait, Roy here has a question. 1 second.
I work in the area of compliance and policy quite a lot. And in these areas where we have a lot of innovative situations, we're transitioning, so to speak. You wouldn't necessarily know what specific kind of component you would go for. Off the shelf is a great place to start, but inevitably you end up having to build some sort of integration into something. And everybody's finding out how to do those integrations in their own silos, as you know, there's a lot of different silos. So in respect to that, I would like to also ask a question from how you communicate between different like-minded groups. And I think that's a great segue from what you guys were saying just before. Is there a kind of modeling integrations groups that you belong to? Is there something that we're thinking about moving forward with in this space where we can sort of discuss the models? If somebody comes up with a better model design than each other, we kind of reach a uniformity? That's my question. Is there anything happening in that space? And that's something I could put out to the floor as well as Peter.
Sorry, I'm not free understand. I'm not free catch the question, but the integration group, something like an industry committee type thing you in mind?
Yes, an industry community. I suppose the GitHub of integration of component mechanical parts.
Well,
modeling. You're
really.
sharing. Yeah, you're sharing models between each other, discussing them. Have a place where there's a forum for them.
Well, yeah, of course, we talk to each single commercial companies who has their similar or who has the capability that can be a good fit with our robotic technology. But as far as I know, we don't formulate any kind of the industry group or the integration group or something like that.
Considering that you move forward with your robotics design so rapidly, my next question is, do you think moving forward that you might find that would be something that you might set up now that you've moved into the local area?
Sorry?
Do you think you might set up a group that works on the modeling integrations for all of this rapid prototyping?
Well, it's an interesting question, but I think it includes the business-wise decision making. So I think I cannot answer directly to you. I think
Thank
it's
you very
Arnold's
much.
responsibility. Yeah, sorry about that.
No, not at all. What sort of software, 3D modeling software, do you use for this, the development of this product?
Oh, the 3D modeling software. Our robot is currently running on the ROS, the robotic operation system. So for the 3D representation, we use RViz, the 3D visualizer of the robotic ROS, the robotic operation system.
Thank you very much.
You're welcome.
I use Kawasaki ROS.
Thank you, Sarah. Are you back from Australia? You're in El Segundo, right?
When I'm in LA, I'm in El Segundo. I work in the 360 workspace there with Moni Van, but near the primary school. But at the moment, I'm in South Australia.
Yeah, yeah.
And I work with Adelaide University and Flinders University with robotics as a industrial engineer.
Very good. We should come back El Segundo soon so we can meet face to face with Mr. Shimizu.
Thank you very much, sir. That would be wonderful.
Okay, we have a question here from Roy.
Yeah, a couple simple questions. First of all, the drive on those motors, the mechanism, are they all harmonic drives?
Yes. Not all. Well, not all, right? GM23 has a harmonic drive. How about 4? Harmonic drive. Do they all have harmonic drive?
Yeah.
Yeah, they do.
So you don't use any planetary gear?
No planetary gear.
To a couple of business relations questions.
Yeah.
So who was the funder of S1 and S2? Who funded your work?
It's purely
Investors?
Self-funded. Well, yeah, of course, we are a startup company, so the cash of the company came from the venture capital or something. But the project-wise, it's funded by the company and partially funded from the METI, the Japanese government.
Oh, okay.
And also we launched that payload with under the umbrella of the ISS National Lab Space Act Agreement. So yeah, some portion of the launch fee was covered by the Space Act Agreement too.
Space Act Agreement in Japan?
No, in the
US?
United States. Yeah, via the
NASA?
NanoRacks actually. Yeah, with NASA, yes.
Through NanoRacks?
Yeah.
Okay. So it sounds like one of your major partners is NanoRacks.
Yes, yeah.
Who else do you consider to be a key partner in this business? Like, do you have a relationship with Astroscale?
Partially, yes, the Astroscale, yes, but we don't have a very strong relationship with Astroscale.
Who do you have a strong relation besides NanoRacks?
Currently, the NanoRacks is the strongest, and the second, no, actually, we are kind of very independent right now.
Okay. Yeah. And who do you consider to be your current and future main customers?
Current and future main customers includes, well, for the on-orbit servicing, I'm pretty sure the Space Force or some DoD and NASA will be the very good customers. And for the space stations, we are talking with, we have talked with several commercial space station developer. Well, maybe you may or may not know, the NASA kicked off the CLD, the Commercial LEO Destination Program last year. No, not last year, maybe in 2021. So NASA funded Blue Origin, NanoRacks, and Northrop Grumman to build, and Axiom to build a commercial space station. So we are talking with them. We have talked with them too. So we are open to any kind of opportunity. Yeah.
And why did you locate in Torrance instead of somewhere else in the United States?
Oh, because there is a huge the aerospace community here, so we like to get.
It's very expensive.
It's expensive. Oh yeah, it's yeah.
If you're going to hire people, you have to pay them a lot of money.
Yeah, but still, it's better than the middle of nowhere.
You have a giant pool of aerospace talent here that is resident in Southern California.
Yeah.
I mean, look at all the companies that have set up shop here, right? Virgin Orbit, Relativity, Rocket Labs. They did that for a reason.
Yeah, that is, we like to have an access to talent in local terrain.
I would like to comment. Yes, John is right. We have, even though some company might move out, like Northrop Grumman used to have a headquarters here, they move out, but new company move in. For example, maybe you didn't know, the SpaceX Hustle, they're actually using formerly Northrop Grumman facility.
Right.
Da Vinci School, Millennium Space System, they all use Northrop Grumman facility. So even though some of the program might move to Florida or some, but the talent is still here. So it makes sense over here. And actually, I know some of the local government, we talk to a local political leader, they're actually very supportive. They want to people to have new company, or if they have to use the facility here, they should do their best to give you the best deal.
Years ago, they tried to move Northrop out. Everybody refused, so they left us here.
That's good. Yeah, the talent. Yeah, as you know, we are chatting with the speaker and John. There's a company right here in Novita. There's a microcosm, and I just explained some of the history between the Southern California community, SpaceX, Elon Musk, and our local AIAA community. I'm not trying to make it. Have you considered? You're talking about the local industry, obviously. We can talk more about this. There actually more new company coming. There's a launcher space. There is a slingshot.
Oh, the launcher.
And also spin launch, and CZ. And actually, they always pop up with some new company here. Very surprised. The vibrant activity, and also the student. Student like Angelina, Fumi, wonderful jobs and very top schools, and also universities. And of course, AIAA has the Cal State Long Beach, UCLA, USC, and UNLV as our student branches. But nearby, we also, for example, you mentioned this. The question is, do you consider working with some of the local university research lab? For example, you mentioned this SEN, Lunar SEN. I know there's a group, Professor Chang, Sunju Chang, there's another member, they're doing some kind of electromagnetic for, the dust absorption system. So they also got very interested in this fine powder or something. So do you have existing, or do you plan to work with some of the local research institute or universities?
Well, there is a possibility, but we currently don't have any active research project with any university lab, something like that. Yeah.
Another strength in this area, even though LA actually a little bit north, you can see Palmdale. That's more aerospace side. You have this Edwards Air Force Base, your Air Force Research Laboratory. So actually, this is a community. So it's not just LA. A lot of people, companies, Lockheed Martin, Northrop Grumman, they also have collaboration with, and the space shuttle landed at Edwards. There's a Vandenberg. So this is actually a very promising area. So it's wonderful you are here. So any more questions online? Dominic, do you have any question? You're working on the Venus lander. Do you think of something that could be interesting, like from your point of view, ESA?
No, this is a very interesting presentation, and I have no question about that.
Okay, very good. So Dr. Van Allen, do you have any comment or question? Maybe it's busy. So if there's no more question, one more thing. So we'll stay a little bit. The speaker will stay here a little bit, and then we have the demo here. So we're not just going to leave right away. So before you leave, that we are going to present this our appreciation for Mr. Seiya Shimizu. So we look for more opportunities. You and your company and AIAA locally, in the local chapter, we are trying to bring everybody together for networking. So as I say, for example, next week we have Dennis talk. It's very exciting for digital domains. It's very exciting. Afterwards, November 14, we are going to have a young professional networking right next to SpaceX. So we are trying to bring the local aerospace community from aerospace, Northrop Grumman, everybody, Boeing, Raytheon, SpaceX all together to have fun and also know each other. So please join us. Let's together, create a very vibrant, aerospace community here and for the nation, for the globe. Yeah, thank you so much.
Thank you very much.
Thank you so much. Appreciate it.
Thank you.
Yeah, so we'll stop the recording now, but welcome to stop by, talk to the speaker, and locally we still have coffee, which is fresh brew, cookie, donut. Please enjoy. Next time we'll bring some good lunch. Today we have the snacks. Please enjoy. And folks online, if you want to speak up, you can continue to do so.
Right. That's exactly what. That's how I look at it.